Welcome to the Engineering Lecture Series Self-Test Revision 13. Your anchor person is Professor Michael C. Ndinechi. The topics covered in this self-test revision 13 are 555 timer, bistable multivibrators, Schmitt triggers, field effect transistor. Please follow me in this engineering lecture series by subscribing to my YouTube channel. Like, share, and drop your comments in the comment section. And of course, we know that this lecture series covers mainly electrical and electronic engineering, computer engineering. And of course, with time, we will add mechatronics engineering. But meanwhile, the ones we have done, we are looking at self-test to help you know the extent you understand the lectures we have been given over this time in the engineering lecture series. We're going to be looking at 6 questions, each question with sub-parts. So the first one is, show the internal working diagram of a 555 timer and label the pin configuration of it. Explain how this 555 timer can be connected to operate as a voltage control oscillator, VCO. And finally, what are the industrial applications of astable and monostable multivibrators? So the figure below, or the figure we are looking at, shows the internal constituents of a 555 timer. It has 2 comparators, which is called, one is the upper comparator and the other is known as the lower comparator. It also has an SR flip-flop, an output buffer, and a discharge path transistor, which is usually an NPN transistor. Of course, we know the work of the comparator. Comparator works to give an output if there is difference between the signal input to the difference between the signal input to the inverting and the non-inverting input of the comparators. So the VCC is having pin 8, labeled as pin 8. The threshold input is labeled as pin 6. The control voltage is labeled as pin 5. The trigger is labeled as pin 2. The discharge is labeled as pin 7. The ground is pin 1. The reset is pin 4. And of course, the output is the pin 3. We put the pins in brackets to show what pin is labeled. And of course, it makes use of the SR flip-flop to indicate when the system goes high. If you look at the SR flip-flop diagram, you see a notch at the Q pin, showing that we are making use of the bar output of the flip-flop. That is the NOT output of the flip-flop. Then the second question says, explain how it can be used as voltage control oscillator. And we say that it can be used as VCO by using the same external connections As for the unstable operation, which is already explained in the lecture where we treated this 555. But the exception is that the voltage control, the variable control voltage is applied to pin 5, which is the control input, known as the count input, as shown in the figure we'll be seeing later. When this is done, the control voltage changes the threshold values of 1/3 VCC and 2/3 VCC for the internal comparators. With the control voltage, the upper value is known as the V control and the lower value is at 1/2 V control, that is half V control. When the control voltage is varied, the output frequency also varies. That is, if we vary this control voltage, so as it changes its value at 1/2 and its value at V changes, and this alters the frequency that is being used. Remember, when it is used as an unstable operation, the thresholds are set at 1/3 VCC and 2/3 VCC. But when it is being used as a voltage control oscillators, the thresholds are set at V control and half V control. So if you look at the figure here, see that this figure on the left is how you set up the 5/5 timer to act as a stable multi-vibrator. So now what happens is that as this V control is increased, the charging and discharging time of the external capacitor, the C external to the left, causes frequency to decrease. And as the V control decreases, the charging and discharging time of the external capacitor, which we label C external, causes the frequency to decrease. Now, if you look at the diagram to the right, you see that the threshold, upper threshold is set at V control and the lower is set at half control. Now, we say that as the voltage increases, the charging and the discharging time of the external capacitor causes the frequency to decrease. So you see the orange side of the signal on the right hand side. Now, as the orange signal goes up from half V control to V control, the rising edge of the signal remains constant until it gets to the point where it starts to decrease. When it starts to decrease, then the trailing edge of the pulse drops and remains constant until it gets to the next point where the orange starts to rise. So with that, you see that you have a regular pulses, which is likely a square wave or pulses, but it becomes regular and continues to rise the leading edge of the pulse, and when it gets to the point it starts discharging, it drops to the trailing edge of the pulse. When it gets to the threshold of half, when it drops to the threshold of half V control, it goes up again. The rising edge will come again. When it gets to the V control, it starts dropping, and the trailing edge of the pulse will continue. So like that, a definite square wave is produced, which makes it a voltage control oscillator, because the control voltage which is applied to P5 determines the output, which is a perfect square wave. Now, question 2 says, what class of oscillators are called bistable oscillators? Using two input NAND logic gates, show how a simple bistable multivibrator can be achieved, and give 6 industrial applications of these bistable multivibrators you may know. So we'll quickly answer. The bistable multivibrator is one that maintains a given output unless an external trigger is applied. We want you to note it very well, that the bistable multivibrator is any multivibrator that maintains a given output unless an external trigger is applied. Now, application of this external trigger causes a change of state, and this output level is maintained indefinitely until a second trigger is applied. So when it starts to oscillate, it remains in a state until you apply an external trigger. If you apply an external trigger, it moves back to the point and remains there until you apply another external trigger. Therefore, it requires 2 external triggers to return it to its initial state. Because they have 2 stable states, they are known as latches or flip-flops, which are used in sequential logic circuits. P says use 2 input NAND gates to design it. If you look at this circuit, you see 2 NAND gates with 2 inputs. So if you look at it, you see that as you toggle the switch between 0 and 1, the signal rises to 1, assuming you start by having your switch is 0, the signal remains at 0. If you toggle it to 1, it goes up and remains in that 1 state until you toggle again for it to come back. So if you look at the output pulse, you see that you have the 0, and when you switch to 1, the rising edge of the pulse gets up and remains in that state until you clock back or switch back to 0. It drops again back to 0. Now, we're saying that this switching can be automated, and depending on the time lag of switching from 0 to 1 and 1 to 0, you can now have different time constant pulses but remains stable as they are. So we say that these bistable multivibrators maintain two stable states but needed two triggering pulses to be able to return it to the original state. These bistable multivibrators have so many industrial applications. First, they are used as flip-flops in digital systems. And of course, we know the importance of flip-flops in logic and sequential design. Say that they act as basic building blocks for latches and flip-flops. That is where you have SR, JK, D, T flip-flops. There are different types of flip-flops. If you follow in our lectures, we will soon get to talk about flip-flops. Two, they are used as memory, storage in static RAM cells and simple memory units to store binary data. They are also used in digital counters and registers as shift registers, frequency dividers, and counters. They also used in the bouncing switches where you need to eliminate multiple unwanted transitions or bounces when you are using mechanical switches. Like in your computers, if you press any key, there is the tendency that the keys we press or the spring supporting the key will bounce back and may cause multiple touches. Now, this bistable multi-vibrators helps you to keep away those unwanted bounces. So it finds good use in switch debouncing. Also, in control circuits is to be, is used as on-off circuits because if it is on, it is on. If it is off, it is off unless toggled again. So in any circuit that you need toggling, you make use of this bistable multi-vibrator. Any system or device where you need to, change mode, so change from this mode to the other, so that when it changes, it remains there until you apply another, effort to change back to the other mode. Then, in waveform shaping, where it converts any irregular input signal into clean, sharp, square wave pulses that immediately, it gets to the threshold and acts. It remains there until it gets back to another threshold. So when it does that, you can now see that the irregular waveform will be, translated into a pure square wave output. And of course, say that it forms the fundamental circuit in designing finite state machines and many other sequential logics. So as we go on in our engineering lecture series, we'll be able to also look at these finite state machines and sequential logic circuits. And of course, it is used in communication systems for data storage, signal conditioning, and in synchronization of the operations of receiver and transmitter. Say that used in memory design, which is very important in your computer systems. Switching circuits, toggle switches. Anywhere you see toggle switch, you must be making use of these bistable multivibrators. Counters and shift register, control circuits, and signal synchronization. Is differentiate between stable, we have been hearing stable, monostable, we'll be hearing that, this bistable multivibrators. What are the differences when we hear stable, monostable, and bistable multivibrators? So, as a student of electronic engineering, telecommunications engineering, as a student of engineering, you should know the difference between these three terms, and want you to also state some special features of a bistable multivibrator. We start by answering the differentiating between the three terms as stable, monostable, and bistable multivibrators. We say that an stable multivibrator has no stable states, and continuously oscillates between two unstable states and continuously producing a square wave output without external triggers. So we've known what oscillators mean. They work without the necessity of external input. So an unstable multivibrator is like an oscillator that produces square wave but have no stable state. So it moves from this to that at random. However, it produces square wave output. In contrast, a monostable multivibrator has one stable state and one temporary unstable state. If you see the difference with stable, the stable has also two states, but none of the two states are stable, and it produces these two unstable outputs without an external trigger. The monostable multivibrator has one stable state and one temporary unstable state, and it requires an external trigger to shift to the unstable state for a fixed period of time before returning to its stable state. In other words, a monostable will start with the stable output, and when you apply an external trigger, it moves momentarily to the unstable state and comes back to the stable state and remains there until you apply an external trigger again. But for the bistable multivibrator, it has two stable states and remains indefinitely in one of the states until a trigger input is applied. Then it switches over to the other stable state and remains there again until another trigger input is applied. So you see, there's a clear demarcation between the stable, has two unstable states, and doesn't need trigger to do that. It does that on its own. Monostable has one stable and one temporary unstable, and remains at the stable until you apply an external trigger. It moves to the unstable one momentarily and comes back to the stable one and remains there until you apply again external trigger. While the bistable has these two stable states. Stays in the first one indefinitely until you apply, a trigger. It goes to the other one and stays there, until indefinitely until you apply another one before it gets back to this. So when you are using them, depending on the application you want, you can now choose to use a stable, monostable, or bistable multi-vibrators. Now, what are the 6 special features of bistable multi-vibrators? You say that it has 2 stable states, quite unlike the stable and the monostable multi-vibrators. Each time, it stays indefinitely in either of the 2 states unless a trigger signal is applied. So it is very good in trigger control switches where circuit changes its state only when an external trigger pulse is applied. And it has memory functionality whereby it can store 0 or 1, which makes it very useful, system in digital electronics. Has very good age sensitivity. When we talk of age, when you have any pulse, you have the rising side, which is called the leading edge, and the falling side, which is called the trailing edge. So if you use bistable multi-vibrator, it gives you a very good response that the rising edge and the falling edge will be, sharp and smooth. Also, this agrees with any form of noise. When we say noise, ripples and that is associated with signals. So say that it is immune to those noises. Due to its regenerative feedback, it resists small disturbances and provides reliable state holding. It also has high stability. Once in a state, it remains there without requiring any continuous input or clock signal to remain there. It remains there unless you toggle it again before it can move to the other stable state. So we say that it is highly stable. And of course, it shows good symmetry, that both states are equally stable and can represent logic levels, which makes it very important device or mechanism in digital electronics. Says, draw the circuit diagram of a basic configuration of a Schmidt trigger using an operational amplifier. What is the main function of this Schmidt trigger? And state the special features of Schmidt trigger. What are the industrial applications of Schmidt trigger? Remember that we are now talking of those basic components that are used in designing electronics and electronic devices. So these multi-vibrators, 5-5 timer, these Schmidt triggers, field effect transistors are most of the devices which are integrated into integrated circuits to be able to perform all the electronic functions your devices perform. So we start with the internal or the circuit diagram of a Schmidt trigger. Now it has an operational amplifier, the inverting input, which is V2 here, is connected, or the V-in is connected to the inverting input through a resistor RE, and the output is fed back through a voltage divider network consisting of R1 and R2 back to the non-inverting input, which is the plus sign, which we call V1. Now, the value of RE will be equivalent to the values of R1 connected in parallel with R2. So when that is done, you see that you continue to either have an output or no output, because as we can see, if we analyze that, there will be always a difference between the V1 and V2. So it's either there is a difference or no difference. So the output becomes either a 0 or a 1. So it gives you a very sharp, output, which is a square waveform. So now, what is the main function of this Schmidt? Say that the main function of Schmidt triggers is to convert any irregular or regular shaped input waveform into a square wave output voltage or pulse. Now, look at it. Assuming I want to use this my voice to control any electronic device, then what that electronic device needs is a square wave input, which makes it to act as the leading edge and act the other way in the trailing edge. So, but the voice signal coming from my voice is very irregular. It may be sometimes peak high and sometimes low. So immediately we establish what is known as the upper threshold and the lower threshold. Anytime this my voice signal crosses the threshold up, it becomes leading edge. Anytime it crosses the lower threshold, it becomes the lower edge of that conversion from my voice. And that serves as the input to that device, which needed a clear square wave to act. So that the main function of a Schmidt trigger is to convert any signal, whether regular or irregular, into a square wave output. So the special features of this Schmidt trigger is that it possesses hysteresis property. Here, the most important feature is this hysteresis property of the Schmidt trigger, because it has two distinct threshold voltages called the upper threshold and the lower threshold voltage. So this prevents false triggering due to noise or small variations in the input signal, because the signal must get to this upper and lower threshold before the system will work. Any small noise or flickers or disturbances will not be able to reach this upper and lower threshold voltages. Therefore, they become irrelevant to the operation of the system. So it's very important feature in the design of any electronic system that requires to be controlled by, irregular shaped input signal. This prevents false triggering due to noise or small variations in the input signal. Of course, we talked about noise immunity because of this hysteresis. If you've forgotten what hysteresis is, you refer back to my earlier lectures in module 11 or so, where we have treated hysteresis. So say because of hysteresis, the circuit is immune to small noises and unwanted input waveforms. It's also very useful in converting waveform. So say it converts slowly varying analog signal into a sharp digital output, digital pulse or square wave output. Useful in signal conditioning for digital systems are used where you need fast switching, provide very sharp transition at the output when the input crosses any threshold level. And of course, it has this bistable action high state or low state and remain there unless toggled again. And it provides symmetry, which is highly needed in many digital designs. That is, it will be symmetry about zero. You have the zero, you have the upper threshold, you have the lower threshold. So the waveform it produces will be symmetry. What you have up is what you have below the zero mark. And because of that, it's very useful in AC signal conditioning. Then, what are the industrial applications of this Schmitt triggers? So, quickly, waveform conversion, converts sine waves, triangular wave, or noisy signals into clean square wave for digital applications. It's also used in the bouncing switches, mentioned this before, so that any noise or spurious signals will not be able to trigger what you are doing. The Schmitt trigger removes them. Signal conditioning in analog to digital circuits. And of course, it's also used as relaxation oscillators. We've looked at relaxation oscillators and what they meant. So you can just use this Schmitt trigger as a relaxation oscillator to get what you want. Of course, pulse shaping in communication systems to reshape a signal that has degraded. So at a point you apply it to Schmitt trigger and it gives you back the original signal the way it is when you are doing your transmission over a long distance and through repeater stations. So it is also very useful in signal processing where you have to do SCADA, that is supervisory control for data acquisition. So supervisory control and data acquisitions, that is, if you have sensors somewhere and you want to collect signals from that place to a central point, then as this signal comes, because they are low and slow in changing, for instance, if you're sensing temperature in a far place and you're bringing it to the station control room, as that signal, because it is a very low amplitude signal, it may degrade more. So you use this Schmitt trigger to get them to what they should be and transmit. And of course, in receivers for radio systems or anywhere you apply phase locked loop systems, you also make use of these Schmitt triggers. And of course, when you are doing your industrial control automations, you you need to toggle, you need to switch, and you switch, you have, a fast response. And if you have noise around that will, penetrate the signal, you make use of the Schmitt triggers so that those unwanted noise or signals will not affect the operation of your system. Then the next question says, explain the three types of field effect transistors, FETs. What are their industrial applications, and why is it that their very high input impedance is a very big advantage over other forms of transistors? We quickly answer that there are three types of field effect transistors: the JFET, which is called the junction field effect transistor; the MOSFET, metallic oxide semiconductor field effect transistors; and the MESFET, the metallic field effect transistors. Now, the first one, which is the junction field effect transistor, consists of a piece of high resistivity silicon that constitutes a channel for the flow of majority carriers. We have mentioned these majority carriers earlier, so we're not delving into explaining it further here. Then the magnitude of this current is controlled by a voltage applied to the gate, which is a PN junction formed along the channel. The field effect transistor gate source junction is operated in the reverse bias region, thereby making the gate current to be practically equal to zero. The MOSFET, which is a metallic oxide semiconductor field effect transistor, depends for its operation on the fact that it is not necessary to form a semiconductor junction on the channel of the FET in order to achieve gate control of the channel current. In the typical normal transistor we have looked at, or diodes we have, PN junction we have looked at, you need it to achieve current flow. But we say that in this one, we do not necessarily need to form this semiconductor junction to achieve the same thing. Instead, the gate electrode is a metallic region separated from the conducting channel by a thin silicon diode layer. Hence, the name metallic oxide semiconductor. Since the gate is electrically insulated from the source drain circuit, its voltage polarity may go either positive or negative without gate current flowing. So it doesn't matter whether it is connected to positive or negative. This allows for the construction of two types of this MOSFET. The one you call the enhancement type, which conducts only when forward biased and is cut off at 0 volts between gate and the source. Also, the depletion type, this conducts in both forward and reverse directions and is cut off only when the gate source is reverse biased by several volts. So if you want to know more, please look up the full lecture in the engineering lecture series. Then the last one, which is the MESFET, otherwise known as the metal semiconductor field effect transistor, is a unipolar semiconductor device that uses a metal semiconductor which works at the Schottky junction level for its gate. We have also looked at Schottky diodes, and This MOSFET works with this Schottky at its metal semiconductor interface for its gate. Now, this distinguishes it from the junction field effect transistors and the metallic oxide semiconductor field effect transistors. This MOSFET is popular for high frequency applications like when you have to amplify microwave level signals used where you need high frequency processing like your cell phones and in radar technology where you have to amplify high frequencies signals that are already weak because of distance covered. Also, this MOSFET offer advantages such as high switching speed and high operating frequencies due to the use of semiconductor materials like gallium arsenide or silicon carbide. They control current flow through a conductive channel by varying the gate voltage, which alters the depletion region at the Schottky junction. So you see, it employs the, the activities of the MOSFET and the JFET to produce, a better quality field effect transistors. What are the industrial applications of these field effect transistors? So they find very useful industrial applications where you have to amplify radio frequency signals and make sure that they operate at minimal noise level. When we talk of radio frequency signal, we are talking of frequencies in gigahertz. So if you are working at that point and needed some level of amplifications, then you cannot use any other form of transistors other than field effect transistors. And above all, because they have high input impedance, it means that the signal input into the next stage does not affect the readings of that next stage. We will see that later in this the C part of the question, because this high input impedance is a term you should know as an electronic engineering student on the implications of high input impedance. Also, one of the industrial applications is in switching circuits, so that they are widely used in logic gates, microprocessors, and power electronics. Of course, in analog circuits, they are used as variable resistors, mixers in your radio circuits, oscillators, modulators in your transmitters. But for power electronics, they are used as switch mode power supplies, where you need to do switch mode power supplies, in motor drivers, and in your inverters. They find wide use in your inverters. Then, overall, radio frequency and microwave applications. When you move up to this high frequency levels, you see that no other amplification device can be applied. You cannot use op amps, you cannot use all these NPN and PN transistors. You rely solely on field effect transistors to do your amplifications and operations at the radio frequency and microwave level. So we say that there are key transistors used in high-frequency circuits for microwave amplifications. They are used in radar systems for signal processing, and in your cell phones for also high-speed signal processing and wireless devices, and in satellite operations for your communications. So you see that the field effect transistors, very important device that you have to know and understand its operation very well. Now, question 6, why is this high input impedance, a very big advantage of this field effect transistor? Say, when a system has high input impedance, the implications is that it has a minimal loading effect. When we talk of minimal loading effect, it means that the device draws very little current from the source. This prevents the source signal from being weakened or distorted. Very important that it draws very little current from the source and prevents the source signal from being distorted. Has any system with high input impedance, we have a very good signal integrity. That is, the source delivers its full voltage to the input rather than being bogged down by a low impedance load. This ensures that the voltage signal is preserved accurately. What we are saying here is that if you have a voltmeter or a digital voltmeter that you are using to measure the voltage across a component, if that meter has very high input impedance, the impedance of that meter will not affect the voltage across the component you are measuring. But if the meter you are using has low input impedance, it becomes part of the impedance of the circuit you are measuring, thereby not giving you the accurate result of the voltage across that component you are measuring, because its impedance is factored into the measurement you are taking. But with high input impedance meter, you will be able to get more accurate reading of what you are taking. So it says it improves interfacing between stages. So in a multi-stage circuit, like in radio circuits, where you have to move signal from RF stage to mixer stage to IF stage and to amplification stage, then you have to make use of stages with high input impedance, so that what happens in that stage will not be affected by what is coming in. So that's what we mean in multi-stage circuits. And also allows maximum signal transfer, such as when we talk of maximum power transfer. High input impedance allows maximum signal transfer, which helps to avoid signal losses along the line. And of course, it helps in making the system energy efficient. Since the device consumes very little input current, it wastes less power from the signal source, because power dissipation is equivalent to P is equal to I square V. So if it draws very little current, then it means that the power dissipation at the point of interface becomes very minimal. So say it is an energy efficient It aids systems with high input impedance, aids energy efficiency. Thank you for being part of this engineering series self-test. We hope that you will subscribe to our channel and get more lectures as they come.